right, because we'll get some people back and we'll have the archive, so it'll be fine.
Well, I know. This was just very incredibly frustrating. Okay, it says we're live. I think we're back.
Yep, it looks like we're live.
We don't have any viewers yet, but the okay, folks. Well, this has been frustrating, and I just want to say, in my defense, this is going to be the last time that I use Hangouts on air for a Google Hangout on air, because it is like this. This is twice now. It's happened to me in a really disastrous way. So my sincere apologies, folks. The Hangout just died, and that's all I can say. Anyway, we're back, and I want to just, I'm sorry, Marco. I want to ask you if you mind. So the purpose of our Hangout, we're talking about these observations from the Hubble Space Telescope, where astronomers have made some observations in various wavelengths, which we will be talking about, where they've seen a displaced supermassive black hole that and by the way, this is hard to do. It's hard to displace a black hole, especially one that's millions of solar masses. So we're talking about the astronomers who made the observations and think that it might be responsible or due to a gravitational wave. And my guests are, I'll just reintroduce them really quickly. Dr. Marco Chiaverja, he's an astronomer at Space Telescope Science Institute. Also right next to him is Dr. Eileen Meyer. She's an assistant professor at University of Maryland, Baltimore County. And also joining me is Dr. Grant Tremblay. He's a NASA Einstein Fellow at Yale University. They're all on the paper. All of the links are in the old Hangout, so hopefully you can follow along, or you still have them up on your paper. Again, I can't apologize enough, folks. I'm so sorry. Okay, so Grant, can you please just do us a real brief summary of the observations that you did and what you saw?
Sure. So Marco, did you want to take this? And
I'm sorry. Did I say Grant? I meant Marco. Yeah. I'm old. I'm all like this now. I've got the vapors. I'm like this.
So as I was saying before, we were taking observations with Hubble, and we were imaging galaxies in the distant universe. And these galaxies are special because they host a supermassive black hole. And that's not a special thing because all galaxies host a supermassive black hole. But in this case, the supermassive black hole is accreting matter gas is falling onto the black hole, and the black hole becomes active. Sometimes these objects are called quasars. And we were interested in studying the physics and the host galaxies of these supermassive black holes. And we observed about 20 of these objects, and 3C186, that is the object we're talking about today, was among them. When we saw the images, we immediately realized that it was weird. It was very strange, because the bright point source, the bright quasar, was not at the center of the host galaxy. And that's what we expected to see. We expected to see a bright point source at the center of the host. In this case, it was not there. So we started brainstorming to try and understand what was going on. We were looking at the images. We took 2 different images with Hubble, one in the near infrared, which for objects at that redshift, we are observing the light emitted in the optical. And we also took an optical image, which samples the ultraviolet light. So we started collecting information, and that was the beginning of the story. The end of the story is the paper that was published today on Astronomy and Astrophysics, and you guys probably have seen the press release that came out last week.
Okay, so you said you did these in the infrared, and what was the name of the galaxy again? I'm sorry.
3C186.
How far away is that thing?
That is 8 billion light years from us.
So it's not in our. So this is a really far away galaxy, and it's one of the. I don't know if is it early universe. I guess it's about halfway, or
yeah.
It's redshift 1, so the scale factor of the universe was about 1/2 the size it was today. If that helps.
Okay. Yes, it does. And do you and so you think that these observations were not what you expected, and so what did you do next? Did you looked at these things, you saw that it had kind of had a strange profile. What happened next?
So the first thing we did was to look if there was spectra taken with other telescopes, because we wanted to understand a little more, and the image was very important. But if you want to see if the object is moving or if it has some strange properties. Spectra is what you have to take. The spectra carrying the information about the kinematics of the gas around the black hole. And we were lucky because we found that the Sloan Digital Sky Survey observed this object, and also Hubble in its early years observed the same object in the ultraviolet. And we looked at the spectra, and we immediately saw that, again, there was something strange, because the emission lines of the chemical elements that are emitted around the black hole were not where we expected to see them. And so that was another piece of information, that there was something strange going on. But it took us a while to put the pieces of the puzzle together and really understand what was happening. From the spectra, what we saw was that the gas that is emitting light close to the black hole was moving at a different speed with respect to the gas that is in the host galaxy. And so, again,
but would you expect that anyway? I mean, if you've got a galaxy with gas, I'm hearing the echo, so I mean, I'll keep it brief. If you see the gases going around in a galaxy and it has a supermassive black hole, would you necessarily expect to see both of those coinciding? I mean, would you expect to see the spectra of the gases, the velocity of the gases of the galaxy, going along with the gases falling into the accretion disk in most cases? Is that what we usually see?
Yeah, well, the center of the emission line should be in the same place. What happens is that
I see.
Galaxy,
I get it.
the gas that is in the galaxy emits lines that are narrow. If you look at it, maybe if you want to display one of the slides that I prepared, I think it's the second slide.
I'll try. I hope the universe doesn't come to an end. Do it. Okay.
Just to show where these emission lines are produced, if that is possible.
Well, in ordinary cases, it would be. But let's see. Let's all hold our collective breath. Okay.
Hey, here we go.
Can you see it?
Okay, so this is just one example of a very famous active galaxy in which the black hole is located pretty much where the bright point source is.
Right here.
Right there. In this case, there is a jet too, but we're not going to talk about that today. And by the way, Eileen
what's this thing?
is the expert of it. So if you go to the next one, maybe actually, this is an image that shows. It's not a real image, of course. It's an artist's view. But at the center, there's the black hole, and all around it, there is this hot gas that is falling onto the black hole, becomes very hot and very bright, and this is called an accretion disk. So this is what I was talking about. Here, the gas moves very fast around the black hole, 10,000 kilometers per second. When it gets closer to the black hole, it moves even faster. But that's the light we see. And if you go to the next one, then
actually, before we do, I just want to make a comment about the fact that we don't see black holes directly because they don't emit any light. So we see a lot these accretion. This is an artist representation, obviously, but this is how we see it, right? I just want to point out that it's what is falling into a black hole and the subsequent jets that are produced that we're actually looking at, not the black hole itself. Correct?
That's correct.
It's important for viewers to know the scale here too. So if you imagine if you define the size of a supermassive black hole by the radius of its event horizon, something called its Schwarzschild radius, the so-called size of this billion solar mass black hole would be about the size of the orbit of Uranus in our solar system. Right, so that's a scale bar on that sort of image. This sort of image goes out to about 50 Schwarzschild radii or so. This is a painting, so there's some artist license taken. But you're talking about sub-parsec scales, so only a few light years in this sort of image, and the size of a black hole relative to the host galaxy that it resides in. If that black hole was the size of a grape, then the host galaxy itself would be the size of the Earth. So this is a huge scale and contrast. Mm-hmm. There's a contrast in scales. Anyway, That was an interjection, but go ahead.
Okay.
And it's called an accretion disk because it's a disk and it's being accreted. And space fans, you know that we just name things, whatever comes out off the top of our head, we name astronomical objects that way. So that's why it's called an accretion disk.
That's
And the
right.
other thing is called a jet.
We name it for what it does. What it does. All right. And did you want to? So here's another another example of a cartoon of what that's sort of a cutaway of what one might expect. A lot of gas and dust on the outside, and jets coming out on either side. Did you want me to show anything else, Marco?
Yeah, well, there are two regions that are important here in this one. If you maybe go to the next one, there's a few. Okay, so the region of the accretion disk and the broadline region, BLR means broadline region, is a region around the black hole where broad lines are produced. Those are the lines that are from gas that is moving at about 10,000 kilometers per second. The narrow line region is much farther away from the black hole, and the gas there is moving slowly. It's moving at a few hundreds kilometers per second, maybe. And so those are two important components of the thing, because from the spectrum, you can see both components. And if they are in the same system, if the black hole is at the center of the galaxy is around it, the narrow line region is in the galaxy, and the black hole is not moving with respect to the host galaxy, then the emission lines have different properties, but they are centered at the same wavelength. And what we saw is that that was not the case. So the black holes seem to be moving towards us at a very high speed, at about 2,000 kilometers per second.
So how much energy would be required to do this?
Let's see. How many supernovae was it in the other video?
Yeah, I think the energy, so the energy to kick a black hole of that mass, we estimated that the mass of that black hole is about a few billion times the mass of the sun. So to kick that black hole at a speed of 2,000 kilometers per second, you would need about 100 million supernovae exploding simultaneously.
Okay, and and I forgive it if you've already said this, Marco, but again, like I said, I got a little bit flustered at the beginning of this hangout, and I want to make sure we mention this. The reason you were able to see this accretion disk or the gas and dust and get the spectral lines that you did get was because you were looking at light that had come from a quasar that was behind it. Was that correct?
No. It was that quasar. It was
the quasar. That was it.
Yeah,
that's what we ruled out.
I see. Okay, thank you.
Yeah.
Okay, and that was what you said was around 8 billion light years from away from us. And so, do you think so? Is there evidence? So these are two merging galaxies that you think were the source of the gravitational waves, correct?
Well, the story we tried to go back and we tried to understand how this was produced. What we see in the image, what we see from the image, is that the galaxy, the central region of the galaxy, is pretty smooth. It's already well formed. So it's not a super young galaxy. It's not a galaxy that is already forming and merging with another galaxy right now. But there is something at a slightly larger distance that looks like a shell or something that is called a tidal tail. That is visible in another of the slides that I sent you.
Okay.
But most importantly, those are features that are produced when we are in the final stages of a galaxy merger. So we see the signature of a galaxy merger, and we see the nucleus that the quasar is not exactly at the center. And that was, see, this is a nice, it's a nice image. These are old Hubble images from a famous press release that was, I think, it was 1996. And
right.
You see, those are 6 quasars that are associated with merging galaxies. And you can already tell that even if these galaxies are still merging, the quasar is already at the center of the largest host. Mm-hmm. It's not displaced. It's right at the center. So this happens very quickly after the galaxy merger starts.
Yeah, maybe that's something we could explain for the public. So it's a bit like if you have a bowl and you drop a ping pong ball in it, and you wait a little bit, you expect that thing to eventually end up exactly in the center. And that's that's why we expect the black hole to basically be at the center. It's a gravitational potential well. It should be there, exactly. So
This was actually an important early press release because it was one of the demonstrations where John Bacall and Mike Disney did a study to look at QSOs, and the idea is, can Hubble resolve the galaxies around them? And at that time, that was not that well known. And so part of this release was that they have different morphologies, and also some of these morphologies are a little bit tortured. So one might guess, because of the way they look, they're all not nice and smooth, that there's something else going on when these QSOs are made. And this is a very important paper early on, like 20 years ago. Oh,
So this was
amazing.
with wide field planetary camera too. This is,
Yeah,
this-
early
So this
days.
Yeah, this is infrared, right, Carol?
No.
But
This
this
is
is
optical.
Optical.
This
again.
is
Okay.
optical.
I
Yeah.
guess it would be 96 is pretty. Yeah, I guess we were still
Yeah, the early days.
pretty rough on the IR time part detectors and stuff then. So
Right.
okay, well, and the quasar part, are they like that? It's not immediately obvious to me where the quasars are in some of these. They just like this one, for
The
example.
one at the center. Always
this
at the center. Yeah, that one.
Oh, this one and this one. Okay, I see. So
Yes.
these are all where the quasars are. Okay, awesome. Okay, so and let's see, what do we? And this is
This is the image of 3C186. It's a color image that is made with the two images we took with Hubble. And basically this is one of the first things I saw, and it was already very strange. Oh, you see, this might be interesting for the people that are listening. There is a lot of red galaxies around it. You see, like a lot of small red galaxies.
these red dots here.
Yeah.
Those are galaxies that are in a cluster of galaxies, and 3C186 is the central galaxy of that
there.
cluster.
So it's surrounded by all of these other galaxies.
Yeah.
That red dots.
So it's
here.
not like it's alone.
No,
I also had a question. You had mentioned that there were earlier observations of this object with Hubble.
yes,
I know
there were.
Chandra and other, and was this seen then?
No.
Ah.
The earlier observations were made with FOS, so
Okay.
it's a spectrograph. There was
And it was-
also
yeah.
there were also some images taken with Pt.2, but the sensitivity of that camera was not enough to show the host galaxy.
It's just a point source, yeah.
And they were also in the optical, so you can't really see the host galaxy at that distance in the optical. We detected it in the near infrared, but in the optical image, we don't see much of the stars around the black hole.
Right, and the ground there. I think there were. Well, of course, there were optical ground-based, and then there were Chandra
Yeah, optical
observations of it too. But none of this showed that.
no hope.
Nope.
Wow.
You need Hubble, yes. Yeah. Yeah, even if you go in the near infrared from the ground, there are large telescopes that can observe in the near infrared and with a very good resolution. But the brightness of the host galaxy of this quasar is so dim that the background light in the near infrared dominates. So there's no hope to see it, not even with the largest telescopes on Earth.
What do you mean by background light? The background light of what?
When you observe in the near infrared, the sky is very bright, and so you need a big contrast between the target you're observing and the light from the sky, and this object is way too dim. You can see the quasar, the point source. Yes, you can see it. That's pretty bright, but you don't see the host galaxy.
Right. So we're pretty much at the limit of what Hubble can see right now. Then with this.
Well, we can go deeper. With Hubble, you can go deeper. You can take longer exposures. These ones were, as I said, like 400 seconds, something like that.
It's not even an orbit of Hubble
Yeah.
time, which is a kind of
Wow. Yeah.
Wow.
Sure.
Yeah, that's sort of the standard unit that people get allocated for observing with Hubble. Grant, I'd like to get you in on this a little bit more. Tell me a little bit about your role in the research and what interests you about what we're talking about.
So I've been kind of following Marco as along with Eileen helping out with this project. It's been a really exciting, very scientifically fruitful survey. Initially designed to survey high redshift 3C objects. By high redshift, we mean about a redshift between 1 and 2, which is looking back from about like 7.8 billion years when the universe was 7.8 billion years younger than it is now, to even younger than that at redshift 2. And we were studying 3C radio galaxies. 3C just means they're in what's called the third Cambridge catalog. They're called radio galaxies, and they're 3C radio galaxies because they're very bright in radio. They're brighter than about like 9 Janskis on the sky, which is really bright in the radio. And so the project that Marco designed and led was not originally designed to look for kicked quasars. We sort of found we were lucky in that sense. And so my role in the high redshift project has been sort of general science, but in this particular project, I was at some telescopes after we discovered this object. And so I did a lot of follow-up observing. One of them with the Palomar 200-inch telescope.
Ah, the old venerable.
The old venerable, this astronomical holy relic, painted battleship gray from
It is a holy relic.
Harbor battleships, yeah. And then we also followed it up, and this Marco would have to like tell me if I'm allowed to say this. No, we say this in the paper. It's fine.
I'll tell you if you're allowed. You're allowed.
I also observed it with Keck, one of the largest telescopes in the world. Keck is on Mauna Kea in Hawaii. And we observed it with this very cool instrument called the OSIRIS Integral Field Unit Spectrograph.
Oh, that is cool.
And what this did is so we have mapped the inner 30,000 light years of this galaxy. And the data that we have is not just an image. It's like an image, but every pixel in the image is a spectrum. And so what we've done is both mapped the broad line region, which is close to the black hole, and the narrow line region in the host galaxy, sort of hanging out with the stars. And we'll be able to sort of map the sort of kinematic decoupling as this black hole is rocketing out of its galaxy.
Okay, hang on. What? Every pixel is a spectrum?
Oh yeah. So this is.
If you're within a pixel, you're going to see an entire spectrum of something.
Yeah, that's right.
Yeah.
Wow.
So what happens is that the instrument takes the light from the pixel and sends it to the detector so that you can see the energy distribution of every part of the image. And that's important when you're trying to look at how, if you just take a spectrum of the whole thing, you get everything mushed together. And so if you want each individual part to see what each individual part is doing and how it's moving, then you need to take each pixel and look at its energy distribution.
Exactly. And so what this will allow us to do is effectively make a movie of this galaxy, but the movie, as we flip through the frames, isn't in time, it's in velocity space. And so we will step through something. So we observed the one of the emission lines of oxygen 3, well, actually both of the emission lines of oxygen 3. And we will be able to step through the sort of velocity structure of this galaxy with this new data set. And so that's what we're working on now with Marco and Eileen.
Okay, before I leave you, I got to just say, okay, space fans, you're not going to get tested on this, but I want to ask Grant to try and explain to us what velocity space is.
Yeah, yeah.
Can you do it for us, Grant?
Yeah, sure. That's probably not the best word to use. Basically, so all we're doing is effectively mapping the Doppler shift of the line through the galaxy. So all of your viewers have stood on a road and heard an ambulance driving down the road, and as the ambulance approaches them, the siren sort of winds up.
That's right, the Doppler effect.
And as it passes you, it winds down. The frequency stretches out, and you hear the tone go down as it passes you. We do the same exact thing, but with light, because light acts like a wave, and it acts the same way as sound waves do from that ambulance siren. And so we will map sort of the Doppler shift of this particular emission line throughout the entire 30,000 innermost light years of this galaxy. And so that's what I mean by velocity space.
So to use your ambulance analogy, the winding up of the velocities, that's velocity. The actual increase in the tone is velocity space. Is the velocity space itself.
Yeah, so all we're doing is looking at gas that's approaching us and receding from us. So the gas that's moving toward us will be blue shifted, and the gas that's moving away from us will be red shifted relative to the systemic velocity of the galaxy.
Okay. Well, I'm reading some of the chat here as you're talking. No one, and that's the guy's handle. I'm not talking to no one. His handle is no one. He goes, I wish I was smart like these guys. Hey, no one, I didn't get it either. That's why I asked the question. So I wanted to make sure that was a difficult concept. So don't feel too bad if you didn't quite get that. Okay, so let's go back to the Eileen. I would like, so can you? I want to make sure we get a good idea of what your of what your role was in this project as well? 'Cause I don't think I've asked you about it. I've been so scattered today.
Sure. So I think myself and a lot of the others, as you notice, there's like a whole bunch of people on this paper.
Right.
Been kind of involved in this larger project, as Grant was referencing, of taking images of 3C galaxies. And so the rest of us were largely working on things like interpreting what we saw after we realized that, I mean, as he said, when you first look at that image, most astronomers will look at that and go, oh, that is weird, like within 5 seconds. So after that, then you have to go through all of the completely generic reasons that thing could look weird. And so that could be something like a foreground star. It could be a background quasar. It could be maybe there's some kind of merger, scenario that we haven't thought through that's really not that, weird. So we had to go through all of that, which took a long time. And so I was kind of involved in those discussions. Sort of in the larger context, I'm a person who's very much interested in actually the jets. So earlier we showed, showed a sort of schematic of what these AGN look like, and a few percent of these accreting black holes produce jets of relativistic plasma. That's actually kind of my area of expertise, which this actual object actually has jets, but we're not really interested in that for this paper. That's not why this object is exciting. Jets are pretty common.
Yeah, okay. So you bring up an interesting point I want to kind of expand on a little bit more. You said that when you see something weird, what astronomers try to do is try to explain what it is. And a lot of times the way they do that is by running a bunch of models and simulation. And Marco, or any one of the three of you could comment on this. Did you try and run any simulations to try and explain what it was? I mean, I know gravitational waves are relatively new as far as a discovery goes, but they're not new as far as a modeling goes. So did you do any of that, or was it just, yeah, it's gravitational waves?
We didn't really do any simulations on the gravitational waves, but we had to do a lot of work on modeling the image to understand where the center of the galaxy was, and also in modeling the spectra. Because spectra of quasars are very, can be very strange. Before I said, oh, the broad emission lines were offset with respect to the narrow emission lines. But then again, that happens often in quasars. There's a lot of quasars that have some broad emission lines that are offset with respect to the narrow emission lines. And it's not always for the same reason. So we had to do a lot of modeling, both on the image and on the spectra, to make sure that we were understanding what was going on in this specific case. The modeling on the image was also done to try and simulate what would happen if there was another galaxy. Because one possibility was that we were observing a galaxy that was in the foreground and was between us and the quasar. And the quasar was behind. And it was moving, but it was behind the galaxy that we were observing. And when you see a quasar, you expect to see a galaxy around it. And if there was another galaxy, then we needed to make sure that we could not detect it. So I ran a lot of simulations to make sure that we could rule out that possibility. So that the galaxy that we were seeing was one galaxy only, and the quasar was flying out of it, and there was no additional object. And that was hard work. And of course, we could have done better if the images were better, were deeper. We hope to get those in the near future. Fingers crossed.
How, with more Hubble time, or are you going to wait for JWST, or both?
Oh, no, Hubble is quite good enough.
Okay.
Well, we need both. We can do a lot of other things with JWST, but actually Hubble is crucial because the Hubble resolution in the near infrared is great. Also, you can't really observe it in the optical with JWST, so we need Hubble. What we can do with JWST in the future, after we know exactly the morphology of the host galaxy, even on a larger scale, we can do the study on the velocity space, as Grant was saying, like mapping how stars are moving in the host galaxy using JWST. But first we need to take a Hubble image to know exactly what this galaxy looks like.
Okay, well, hopefully you guys could that's your takeaway for today. Two things. Black holes can be kicked around by gravitational waves, and we've learned what velocity space was. So you're welcome. That's all I'm going to say. Okay, so I'm reading some of the comments, and there is a Hans Milling is commenting. We have an old gray telescope like that in Copenhagen. Open to the public every Wednesday during the winter. That's awesome. I hope you guys go out. Definitely use your local telescopes.
Absolutely.
And because they're a treasure, you just really can't get that stuff anywhere else, and you don't got to buy one yourself, which is always better. Achilles 308 is asking, could you rule out there being a third supermassive black hole, and the two which spiraled in from the galaxy merger got kicked out before they merged? Does that make sense?
Yeah. So, yeah, this is an interesting question. So one thing that can happen, I'm not sure if this is exactly what this person meant, but one thing that can happen is if you have 3 black holes, and those 3 black holes, for example, they can be the central supermassive black holes of 3 different galaxies that are merging. So when they get close to each other, at some point, the smallest black hole gets kicked out. It's a phenomenon that is called gravitational slingshot. It's something similar to what we do when we send a probe to a planet, and we make it go near Venus, for example, and then gets a kick, and it gets sent out to Jupiter or Saturn. Yeah. You use the gravitational field of a massive object to increase the velocity of the smaller one. So this is a possibility. The reason why we think this is very unlikely is because the quasar has a supermassive black hole that is very, very massive. It's among the most massive supermassive black holes in the universe. So, and those are rare objects. So in order for this scenario to be viable, you would need 2 additional black holes in the same system that must be more massive than the one we see by a significant amount.
More massive than the most massive one.
Yes, yes.
Okay.
So, and for sure, what we know is that there is no other active black hole in the system, because another possibility is that you have 2 AGNs, 2 active galactic nuclei. It's called dual AGNs. There are some in the nearby universe that are known. And we don't see that. So black holes that don't accrete gas are very hard to see because we don't see a black hole. We just see the gas that falls onto it. But as I said, it's a very unlikely scenario because you would need more massive black holes than the one we see.
Okay, very good. So Adam Synergy's asking.
So just before that question, so one thing I didn't understand from reading the paper and also looking at the press release is the thing that happened that kicked this thing out, was that asymmetric in some way?
Had to have been, yeah.
Yeah, there is a slide if you want to show it that may show the mechanism a little bit better.
Okay, I'm scared, but I will. Don't go anywhere, people.
I'll keep
sharing my screen. Crossed. Yes, thank you. Share, make me big. Okay, and present. Okay, I have this up. Do you see it?
Yeah. So you go forward. I think it's not the next one. The one after this. One more. One more. No, go ahead. Go to the end. These are technical details. This one. Okay. Oh. So you see the 2 black holes that are in spiraling. They're getting closer to each other, and while they do that, they lose energy by emitting gravitational waves. Those waves, that the blue things you see are the representation of the gravitational waves. What happens is, if the 2 black holes are exactly identical, the whole process is symmetric. The gravitational waves are basically going to expand like on the surface of a sphere. If the 2 black holes are a little different, for example, if one of the 2 black holes is a little smaller, or if one is rotating faster than the other, then the emission of gravitational waves is not symmetric. If you click, then it will show you 2 arrows. And okay, so this is basically it's not exactly the power of the gravitational waves, but it gives you an idea of how much power is emitted from each of the black holes. So let's say the more massive one is the one associated with the larger arrow. And again, it's more complicated than this, but it's just to give a representation of the thing. So basically, the emission is asymmetric, and when the two black holes finally merge, the system recoils. At that point, it's like shooting a gun. And that's what we think. It's a very efficient mechanism that produces a lot of energy. The 100 million supernovae, the energy of about 100 million supernovae that is needed to kick this black hole is only a tiny fraction of the energy emitted by the gravitational waves in this process. But that's what we needed to kick it out. And so the next slide shows you, well, we lost you. Tony,
No, I'm here.
Okay, yeah. If you click on it, there is a little animation. You see the host galaxy and the black hole, and the active nucleus just flies away.
Oh, okay.
It's a representation of what happens.
Okay. All right.
Yeah.
Well, good. So let me go back to the Hangout. Please don't go away, Hangout. Yay, I'm back. Okay, good. All right. So I want to get to some more questions and comments before we run out of time. Where did he go? Adam Synergy is saying, and I want to get to this because I believe it was Grant that was saying that this was extremely bright in the radio wavelengths. He goes, we want deeper exposure. Let's get ALMA on the case. Now, ALMA is a telescope that's got a very high resolution, right, Grant? So what could you expect to learn anything from a telescope like that?
Yeah, absolutely. So ALMA can do really extraordinary spatial resolution, 0.03 arc seconds at its. So ALMA is an array, an interferometer. So it's like taking a big mirror, and shattering it into 66 pieces, and then taking those 66 pieces and spreading them over about 25 kilometers in the highest and driest desert in the world. And this mirror is sensitive, and your receivers on these individual arrays are sensitive to sub-millimeter wavelength light. So this is higher frequency than radio, but between far infrared and radio.
Okay.
And what it does is, in the low redshift universe, it can map cold molecular gas, cold molecular hydrogen, so from the fuel from which all stars are born. And it can do the same thing in this galaxy. It's at a higher redshift, so it would be observing different transitions. For example, it could do C2. But we would get really spectacularly high spatial resolution. And the cool thing about ALMA is that sort of movie that I talked about in velocity space, ALMA can do that, but at extremely, extremely high spatial resolution. So absolutely, we should get ALMA on the case.
Oh, well, are you gonna? Have you applied for? Okay, good. I recently asked that because I recently did in the Space Fan News where I learned that ALMA is one of the most oversubscribed. It's part of the Event Horizon Telescope and a bunch of other things, and it's also
really cool. As someone who has used ALMA, it is like the most fantastic thing I've ever used.
I know. The more I learn about it.
But
yeah.
No, of course not. But it is pretty great. That's for sure. Philip W. has got a question for the panel. And welcome back, Philip. It's good to see you again. Hi, Galaxy. I see you too. It's good to see you back as well. Thank you guys, by the way, for finding us again. Is it possible to know in which direction the black hole moved when it was knocked out of alignment? Did it move along the accretion disk? And if so, is there evidence of this?
So when the black hole was kicked out, the accretion disk was probably not formed yet. We know that because we know when the AGN started, when the black hole became active. That actually happened about 100,000 years ago. So it's a very young AGN. It's a very young active nucleus. The accretion disk took a little while. We don't know exactly how long to form, but basically, at the very beginning, there was gas around the black hole. The two black holes were at the center of it. They merged, and then the black hole was kicked and dragged away the gas that was around it. After a while, the gas settles, and the accretion disk is formed. The direction of the motion, we don't know exactly because we all see 2 dimensions, so we all see everything in projection, but it's definitely moving. It has a component that is moving towards us. So it's not coming at us. It will never get to us, so don't worry. But it's coming in our direction, probably at an angle, because otherwise we wouldn't see the offset in the image, but it's in our direction.
Okay, and we're going to go back to basics a little bit here because you guys are asking questions. I want to make sure we get to them. There's some really great advanced ones. There's also some simpler ones, and I want to get to those as well. Kungenson, sorry man if I messed that up, is asking what's a quasar, and by extension, I want to ask what's the difference between a quasar and a quasi-stellar or a gamma ray burst. I'm sorry.
Black hole size is the main thing, but yeah.
Yeah. Okay, so a gamma ray burst is a smaller quasar?
I spoke too much.
Okay. How about you, Grant? Can you give us an idea of what a quasar is?
Yeah, sure. So the thing you need to know is that in order to grow a supermassive black hole, you have to liberate something called gravitational potential energy. And all that means is that you can't grow a black hole for free. So as matter falls, so say you have a black hole and matter is falling onto it. We call it, matter is accreting onto it. What a quasar is, yeah, it's feeding, yeah. All a quasar is a supermassive black hole upon which gas is falling at something close to what is called the Eddington rate. You don't really need to know what it is, but just the maximum amount of gas that's able to fall onto this black hole is falling onto this black hole. And what that does is this black hole is really massive. This is about 1 billion times more massive than our sun. Remember that the sort of size of the event horizon is about solar system scale, so about the size of Uranus. But you have this enormous disk that's many, 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 many times larger, up to even light year scales in some cases. But in order to conserve angular momentum, the accreting material around the supermassive black hole pancakes into this thin disk, within which you have an enormous amount of dynamical friction, a very high Kepler speed or orbital speed for this gas because it feels this immensely massive supermassive black hole in the center of this deep gravitational potential well. And so you get a lot of energy there. And so what that does is that it can, the amount of light emitting from this very, very small volume, remember that the black hole is about the size of a grape relative to the size of the Earth, if you're comparing the size of the black hole to its host galaxy. But the light coming from that super, super tiny volume, that little tiny volume around your little grape, is outshining the light from the entire host galaxy in many cases, and in this case for sure. And that's what's called a quasi-stellar object or a quasar.
And these are the brightest objects in the universe, right?
And depending on how you define it, yes.
But depending on the wavelength, I suppose. Yeah.
They're up there.
Yeah, they're way up there. And just for me, a gamma ray burst. You said Eileen was just a smaller version, maybe.
Yeah, gamma ray burst. Actually, for those of us who study jets, there are some interesting similarities, although there's a lot of differences. But you're looking at something that's a collapsed solar mass type object. So you're looking at something that was a star basically. So 10 to the 9 difference in size, in mass. So it's
okay, great. Well, thank you.
Also, I was going to comment that these people were all in 4th grade at the time, but the point of the name of quasi-stellar, because I remember the name quasi-stellar was because at the time from the ground they could not be resolved, and they were tremendously bright. We knew they were way far away, but they were like a star. So sort of like a star, quasi like a star. But then that's why the 1996 observation by Bacall and Disney was so important, because it showed they are not stellar. So that started the whole thing.
The accretion disk is still stellar.
Yes.
Yeah, but you see that those observations were great because they showed that there was a galaxy around.
There is, what? Because people are like, what is it? Yeah,
there are very small sources, very bright sources at the center of galaxies.
And we wouldn't have got quasar from that if we didn't do it anyway. So that's a cool name, and we needed that. So I'm glad it was started that way. So Philip W. is asking, can modeling help identify similar galaxies without specific inspection? Could it be found by a single pass by a ground or space-based telescope? And I guess I'm going to reword this a little bit. can you comment on how common you think this is, guys? How common is what you're observing is? I mean, I know you've got this one event, but yeah, how common do you think it is? And can you just model this to find similar galaxies without actually finding them? So that would be Philip's question.
Should I?
Yeah.
Should I go? Okay.
Go ahead, Marco. That's what you get for being lead author. You get
objects like this are thought to be very rare. First of all, you need two black holes, two supermassive black holes that are merging. This in the distant universe, when the universe was young, was happening often. In the local universe, right now, it probably doesn't. So you have to look at objects that are far away. That's not a big problem. The problem is, in order to kick out a black hole at a speed that is significant enough to make it clearly offset with respect to the center of the host galaxy, you need a lot of energy. And so you need a combination of different properties of the two black holes. As we were saying before, the two black holes don't have to be identical, otherwise nothing happens. The gravitational waves are symmetric and the black hole is not kicked. So there are some people that did very nice simulations, and they saw that the probability to have something like this in the encounter of two supermassive black holes is about 0.03%. 0.03% is a small number, but if you consider how many galaxies there are in the universe, you may have a lot of these going on. The problem is finding them. And there's another problem, because you need spectra and images to see that, because you need to see the quasar offset with respect to the center of the host galaxy, but you also need to see that it's moving. So if it's moving on the plane of the sky, the spectra don't tell you anything. Because
oh no, not another one of those. Oh,
yeah.
We have that with the transit method on the exoplanets too.
Yeah, and on the other hand, if the black hole is moving along the direction of the line of sight, the spectrum shows you something, but you don't see that it's offset with respect to the center of the host. So you need a combination of both. Probably like moving around 45 degrees is the best option, but those are rare. So yeah, they are hard to find, and there have been only a few candidates of this type published, probably less than 10. This one we think is a very good one, but of course we need to understand it better. It's not the end of the story.
Well, of course you need more observations, right?
Of course.
Yes, we need more observations. Yeah, of course. Okay, real quick, two more questions, then I'm gonna have to let my guests go. I started a little bit late, so thank you guys for staying with me. Nadia Blackman is asking, what's the difference between a quasar and a blazar? Then, if we talk about quasars, what's a blazar? What's the difference?
Eileen.
Okay. Quasars are generally just very, very bright, active black holes, right? The types that have jets, which we mentioned was a few % of these. And not only that, but the jet has to be beamed at us. It has to be pointing towards Earth. When that happens, those jets produce something called synchrotron light. And not only that, but the plasma that's emitting that light is going very close to the speed of light, so very close to 1c. And that produces something that basically, there's a relativistic effect that pushes the light into our sort of viewing cone. So this is very, very weird, but people learn about it when they're graduate students in astronomy. So basically the light is sort of all bent forward like a flashlight. And when that happens, that's called a blazar. So those objects are also very, very bright, but at other wavelengths besides optical. So if you look in the radio, you will see this monstrously bright object. If you look in the X-rays or even the gamma rays, you will see this monstrously bright object.
Okay, and just there's a quick comment I just want to give to Anirudh Dua is asking, are black holes invisible, please? And then the answer is they are invisible unless they happen to be near something that is falling into them, and they like gas and dust, things like that, and as this material falls in, they can let off infrared radiation that we can see. So really, black holes aren't observed directly as much as they are inferred by what's going on around them. Now, the Event Horizon Telescope, which I talked about last week in SFN, is planning to directly image the event horizon of Sagittarius A star at the center of our galaxy, but those are done at radio wavelengths. but it is you. So far, no one's seen one directly. They are usually inferred. Okay, guys. Well, I guess we will stop there. You guys, thank you all for the great comments, and thank you also for sticking with me. I appreciate it. I apologize for the technical issues that we had earlier. I just want to leave with one final question for you three. What's next, Marco, Grant, and Eileen? What do you guys, where do we go from here? Your paper just came out today. By the way, the link is in the old one. So go to the old Hangout. So please go download it and read it and check it out. What's next? I'll have each of you comment.
Well, I think both Grant and Eileen already talked a little bit about it.
Yeah.
We need to get more observations, and ALMA and the Keck data we got some time ago, we will work on them, hopefully sometime soon. But ALMA definitely is something we want to do. We also want to take new images with Hubble to see the host galaxy better. We need to do some work, hopefully with some collaborators around the world, on modeling from a theoretical point of view what we think happened. And I think we will work for the next few years, try to collect new data and try to rule out other possible explanations that are still viable at the moment, and understand this object better. If it is what we think it is, it's a very important observation we made. So we have to work hard to make sure that we are understanding really how this has been produced.
Okay, good. And how about you? You want to comment, Eileen, real quick, or do you feel like you already done that? Grant, same here. You're going to be.
This galaxy is a gem that we'll keep studying for years to come.
All right. Well, and you all, I just want to mention, you told me before the Hangout started that you are heading to the Harvard Center for Astrophysics, right?
I'm here right now.
Oh, you're here there.
Yeah.
Okay, and you're going to be there soon. Well, good. Congratulations and good luck in your future job, and I appreciate that. And thank you all for taking time out to do it. Well, Carol, do you want to comment a bit about what might be coming next, or are we still planning on what's coming next?
We hope we're going to have some commentary from folks who are using SOFIA or who will use SOFIA, and what their program plans are. And that's being arranged by the SOFIA project. So hopefully in April.
That's a great telescope.
Yeah, so we'll talk to some of them about that.
Okay, good. And once again, folks, I want to thank you all for your patience in today. I just want to say that we are working, now that these Hangouts are being supported and funded, we are working on improving the production quality. My sincere apologies for what happened earlier. And next week, starting with the Footsteps to Mars Hangout, we are going, going to be discussing some of the health effects of getting us to Mars, and what are some of the medical considerations for going to Mars and keeping the astronauts alive once they get there. We're going to be streaming for the first time on YouTube, like we always do, deepastronomy.com/live, like we always do, but we're also adding Facebook Live as well, and that'll be done on my Deep Astronomy page. So go to facebook.com/deepastronomy, and it will be announced there as well. So that'll start next week, and then over the coming weeks, we're going to be gradually improving what we do and how we do it. So we hope that so your patience won't go unrewarded. Okay, so we will get this done. Thank you all for your great chats. I appreciate it. And Hans Milling reminded me on deepastronomy.com I need to remember to do the periodic introductions. When I get lower thirds back, I won't have to do that. So hopefully that'll begin next week. So again, thank you all very much for watching. On behalf of Carol Christian and our guests, thank you so much for watching. And as always, keep looking
up.
Thanks for having us.
Bye-bye. Thank you, guys.
Bye-bye.